record this. Okay, hopefully you guys noticed that when we looked at Algebra 2, okay, for those taking both, when we looked at Algebra 2 units, and let me share my screen. Awesome. Okay, when we looked at the units for Algebra 2, for semester 2, a lot of it is things that we've already at least touched on in semester 1 of pre-calc. Okay, so these rational expressions, radical expressions, exponential logarithmics, right? We've touched on these 3 already in pre-calc. But obviously, as I told you, Algebra 2 sometimes has a lot more details, right? It gets down to the nitty-gritties versus when we looked at these in pre-calcs, we kind of just hit the highlights there. All right, so hopefully though, for you who are in both, these first 3 sections are hopefully not too terribly difficult, okay? And as I told you in class earlier, you're gonna have about 3 units a night that we're gonna cover, okay? So 3 units a night, Monday through Thursday, and then you're gonna have about 3 or 4 that you have to cover on the weekend, okay? With pre-calc here, looking at our units, we are starting at trigonometry, right? And we're working through trigonometry, getting ourselves to complex numbers, all right? So there's not gonna be a whole lot of overlap between this semester of pre-calc and this semester of Algebra 2, okay? You'll have a little bit of trig right here at the end of Algebra 2, but obviously you will have been working through that throughout, okay? So hopefully the Algebra 2 class is not as labor intensive for you all this semester, and hopefully it just re-solidifies what you've already learned, and it's a pretty good time, okay? Moving forward here, all right, looking at our schedule, So like I said, in Algebra 2, you've got about 3 a night, but for trig here, if you look, we only have about 10 units, 10 lessons per unit, or 10 sections per unit. Oh, sorry, I lied to you. We have about, just kidding, it's way less. We have about 5 units per, 5 lessons per unit. That does include the testing unit. Okay, that does include the testing lesson. Okay, so what we're gonna do is we're gonna cover about 2 of these lessons a day, all right? And if we can cover 2 lessons a day, that means that we will be done in 3 weeks and you will have everything completed. Okay, so our goal is to have about 2 lessons a day. Okay, again, about 2 lessons a day for, 4 or 5 days, depending on. My goal is for you guys to not have any weekend homework in pre-calc. Okay, so my goal is to cover 2 a day and for you to stay on schedule so you have no homework during the week, during the weekends for these next 3 weeks, okay? So this is kind of the breakdown of our schedule, but basically we're gonna cover about 2 units a week. So you're going to be taking about 2 tests a week. And that's, again, this is the recommended schedule so that you can finish within 3 weeks. Again, if you fall behind, not the biggest deal in the world here, right? You will have the opportunity to make anything up in week 4. All right. But again, looking at our schedule here, okay, the practice and discussions, those are still going to be extra credit. So practice and discussions are going to be extra credit. All right. And then we are only going to take the CSTs, the computer scored tests. We are not going to take the TSTs. So we are only taking computer scored tests. Practice and discussions are still going to be extra credit. And you should have gotten an email from your Apex teacher. Again, they're offering extra credit if you watch that welcome video or, send them whatever videos. So again, look to that email from your Apex teacher. And again, you should have gotten that email. So you should already have, access to Apex. Okay, you should have already had access to Apex starting now. All right. So again, we're going to try to cover about 2 units a day. So without further ado, does anyone have any questions before we get started here? Okay, awesome. I see 5 cameras on. I've got one person without their camera on, so you might want to fix that for me before. All right. And if you are walking along through Apex with me as you're going, that's totally fine, right? And if not, not a big deal. All right. But let me go to share my screen with you here. Oh, and one final thing that I mentioned in the earlier class, I just want to be fair and make sure I mention it. When I looked at your grades, okay, when I looked at Apex grades versus how much time you spent on Apex, all right, the people with the highest grades spent around 50 to 70 hours on Apex, okay? That means that they went back through, they took their time, because what you're supposed to do is, right, what the policy for this is we spend an hour and a half in class going through stuff, right? Then you're expected to spend an hour and a half outside of class working on Apex, whether that's quizzes, tests, practice problems, checkups, studies, right? All of that different stuff. So you're expected to go through that about an hour and a half per night, okay? So that should be where you're averaging at there, okay? So if we get right into this here, we're going to start with introduction to trig. Okay, we're going to start with introduction to trig. So if we look here at our introduction, okay, this video here is just going to show you a bunch of different highlights. Okay, so Pythagorean theorem, angles and radians, going to talk about, I believe, the unit circle, okay, arc lengths. So all this is talking about here is this thing called trigonometry. Okay, it's all these concepts that have to do with trigonometry. All right, and let me look at who I'm looking at. Hey, Quinn.
Yes.
Did you take geometry already, I'm assuming?
Yes.
Perfect. Was it just straight geometry or was it geotrig?
Geotrig.
Perfect. Okay, so hopefully then a lot of these concepts are familiar. We'll just dive maybe a little bit deeper. And so hopefully it's not too terribly difficult for you guys since you already had geotrig. All right. But basically, we're going to talk about these trigonomic functions. We're going to go a little bit, hopefully more in depth than what you guys did in class. So again, if a lot of this seems like review, great. Keep building on that foundation that you have because you're going to need it for the rest of this semester. And then obviously as you go into calculus later on. All right. So first off here, we have right angles. Okay, we have right angles. So looking at this, all right, again, I know we talked about this in Algebra 2, but talking about shadows here. So trying to figure out how tall a tree is.
During a typical day, the position of the sun in relation to an object will determine the length of a shadow cast by that object. Here you see that as the sun moves, the length of the tree's shadow can change from very short to extremely long. In a situation like this, you can calculate the length of the shadow by simply walking the distance. You can also estimate the angle as shown. Is this enough to enable you to calculate the height of this tree? It turns out that the answer is yes, it is. To begin to understand how such a calculation would be possible, you must first gain an understanding of trigonometry. By the time you finish this lesson, you will be able to answer all sorts of questions about distance, angles, and lengths as they relate to right triangles.
Okay, and perfect, right? So again, I know we all have, pretty much all of us have a cell phone at this point, and a lot of us have iPhones, or I know you all have iPads, obviously. And Apple does now have that feature that kind of lets you trace things. But as we know, that's not always accurate, right? So for something like this, where maybe it doesn't matter, you can generally use your phone, all right? But if you want to actually get more accurate and more precise as to what you're looking at, right, you could use some trigonomic functions that we're going to learn here. All right, so starting off first, we're going to talk about right triangles. Okay, we're going to talk about right triangles. So hopefully you guys have learned about the Pythagorean theorem, right? And it comes from a guy, Pythagoras. And basically what it has to deal with is it deals with measuring angles and lengths of this right triangle. Okay, and a right triangle is one where it has a 90-degree angle. All right, it has a 90-degree angle. And then we usually label the sides A, B, C, right? A, B, C, where A and B are what we call the legs of the triangle, and then the value C here is opposite of that 90-degree angle, and we call that the hypotenuse, right? Okay, so looking at Pythagorean theorem, right, we'll watch this video here, but you should hopefully know it's going to boil down to a squared plus b squared equals c squared.
The Pythagorean theorem tells us that the sum of the squares of the lengths of the legs is equal to the square of the hypotenuse. In symbols, this is written as a squared plus b squared equals c squared.
All right, so again, in English, what he said was the squares of the legs added together is going to equal the square of the hypotenuse, right? So again, A and B are the legs, so we square them. We add them together. That gives us the sum of the square of the legs, right? I know it's confusing. All right, equals the square of the hypotenuse. So C is our hypotenuse length, so we squared that.
Geometrically, this theorem tells us that if we add the areas of the two smaller squares, we will get the area of the largest square in this diagram. Now assume that we only know the length of two sides of a right triangle, and we want to know the length of the third side. We can use the Pythagorean theorem to solve for the third side. If we solve this equation for C, we find out that C equals +5 or -5. Ruling out -5 is impossible for a length, we see that C equals 5.
Okay, awesome. So pointing out there, again, you have to be careful and you have to know what's realistic, okay? You can't just multiply something or divide something and get a value and then just go, yep, that's right, totally, because I got it in my calculator, right? So once you get that value, because we know when we take the square root, we get the positive and the negative version, you have to use some logic there and say, okay, great, well, I can't have a negative length, so that's got to be a +5.
As this example shows, it is important to remember that the Pythagorean theorem is true only for right triangles.
Okay, so that's going to be one of the requirements, is it has to be a right triangle. Okay, has to be a right triangle. All right, so then moving forward here. Okay, if we were to be running a track, okay, and we have to follow this path here. All right, so suppose your school has a football field that measured 160 by 300. Okay, again, this is where logic comes into play. All right, if I told you 160 by 300, looking at this, obviously this line here, this white line, is going to be the larger length. That's going to be your 300. And the red line here is going to be your 160. Again, using logic, you have to make sure that that's a big part of your mathematical skills there, is using some logic. All right, so it's asking, we have to run 5 miles. We have to run 5 miles. How many times would you need to run this path, this triangular path here, in order to run the 5 miles? Okay. So again, using logic, you have to know that this longer length there is the 300 and the shorter length there is the 160. All right, so this is the path that we're run. So the first question we have to answer then is obviously, what's the missing length here? All right, what's the missing length here? And we're going to use Pythagorean theorem, but for the sake of time, I'll just put a 1 there. All right, the correct answer is 340. Okay, and you might ask, how did we get that? Okay, well, looking at the calculation here, a squared plus b squared equals c squared. So we add that together, we get 115,600 equals our c squared, or diagonal squared. So when we take the square root of that by plugging it into our calculator, we get this value of 340. Okay, so then the next step is okay, if I run this triangle, how long am I running? Okay, or what's the length of one lap? Okay, so again, I add them together. So 160 plus 300 plus 340. So if I run this triangular lap, I'm going to be 800 feet. Okay, and if there are 5,280 feet in a mile, we can figure out how many laps it's going to take. All right, now this right here, this dimensional analysis should look very, very familiar from what you did in your chemistry classes. Okay, again, just to remind you what dimensional analysis is, it's unit cancellation. Okay, you have things that are equal to each other that can cancel out. So For example, here, I have 5,280 feet. That's what's in 1 mile. Okay, that's what's in 1 mile. Now, I know that one of these laps is equal to 800 feet. So if I have feet on top and feet on bottom, or in the numerator and denominator, I can cancel those guys out. So what I do is I multiply 5,280 by 1, that would be on top, and 800 would be on bottom. When I simplify and I cancel my feet, I get 6.6 laps per mile. 6.6 laps per mile, which means I need to go around this 6.6 times in order to equal 1 mile. All right. Now, in order to do that, it says, how many would it take to be 5 miles? All right. How many laps will it take to be 5 miles? So if I just continued my dimensional analysis here and I multiplied by 5 miles, that's going to equal, well, miles will cancel with miles. I just multiply 5 by 6.6, and that's going to give me some value in laps, right? That's going to give me some value in laps. So if I just type in 1 for the sake of time, okay, 5 times 6.6, that's going to give me 33 laps. Okay, 33 laps. So again, hopefully this is bringing up some things that you maybe learned in geometry or your geotrig, and then hopefully it's reminding you of things that you've done in your chemistry courses. All right. So then with right triangles, there's a couple special triangles that we want to highlight here. Okay, again, just maybe reminders all, but it's still very, very important. All right, so the first one is this 45, 45, 90 triangle. All right, and what that means is you've got a 45 and 45 angle, and then obviously that 90 degrees for that right triangle.
Since the diagonal of a square bisects, divides in half, the angles of the square, the angles formed measure 45 degrees is marked. This kind of triangle is referred to as a 45, 45, 90 triangle. You can use the Pythagorean theorem to write the relationship between the legs and the hypotenuse of this kind of right triangle. As these calculations...
Okay, so pause. I know she's going a little quickly there, but obviously what she said was it starts off, if you start off as a square, okay, if you draw a diagonal line cutting that square in half, you end up splitting that 90-degree angle. Okay, so you end up with 2 45s. So we end up with this thing called a 45, 45, 90. All right. And if you think about it, since these have the same angles, they have to have the same length. Okay, they have to have the same length of the triangle. And if we just look at Pythagorean's theorem, normally this would be a squared plus b squared equals c squared. All right, but since they're the same value, we just say a squared plus a squared. That gives us this 2a squared here. Okay, that gives us this 2a squared here. All right, and we can say then that 2a squared is equal to c squared, right? 2a squared is equal to c squared. Basic addition principle there, right? We have a squared plus a squared, that gives us 2a squared. All right, and then what we're going to do is we're going to simplify that.
Each leg of a 45, 45, 90 triangle.
Okay, so when we simplify to get a by itself, we can divide by 2, and then we can take the square root. And then we take the square root. Remember, we have to take the square root of everything. So we would have this square root over the entire 1/2 c squared. All right, but that's like saying square root of 1 divided by square root of 2 multiplied by square root of c squared. So when we simplify that, the square root of 1 is 1, the square root of c squared is c, but we cannot simplify the square root of 2 to anything smaller. So we're left with a equals 1 over the square root of 2 multiplied by c.
Triangle is equal to 1 over the square root of 2 times the hypotenuse.
Okay, and since they're both a values, it's going to be the same thing. All right, and no, you don't have to memorize this, right, by any means, because all you'd have to do is just re-walk through the process that we got to. Okay, knowing that these are the same length for the same angle is what's going to be the key here. All right, so 45, 45, 90, you have the you have the same length of the legs, they end up having the same value, which is this 1 over square root of 2 times by c. All right. Looking at a slightly different triangle here, we have a 30, 60, 90 triangle. 30, 60, 90 triangle. All right. And what this starts as, or what's the easiest to understand here, is if we look at something that's a 60, 60, 60 triangle. Okay, and they're going to do the same thing. They're going to cut this down in half.
Consider this equilateral triangle with side length C. Since the altitude of an equilateral triangle bisects the 60-degree angle.
Okay, again, I know that was kind of confusing. So what she's saying is when you draw that line straight from maybe one of the angles here, and you could have done it for any of them, right? But when you draw it, it bisects. Okay, it now makes a 30, 60, 90. Okay, in order to form that 90-degree angle, we have to cut one of those 60 degrees in half. Okay, so now we have C divided by 2 because we took this and cut it into 2 parts. So we have C over 2, and we now have this value of B. It also could have been A, whatever, but we use this value for B here.
And is a perpendicular bisector of the opposite side, you obtain a 30, 60, 90 triangle. This calculation shows that the short leg of a 30, 60, 90 triangle is 1/2 times the hypotenuse. To find the length of the longer leg, you can use the Pythagorean theorem to write the relationship between the legs and the hypotenuse. As these calculations show, the longer leg of a 30, 60, 90 triangle is equal to the square root of 3 over 2 times the hypotenuse.
Okay, so again, same thing here. All we did was we understood the relationships that we have, right? So this becomes C over 2, and we understand that A squared plus B squared equals C squared. So A squared plus B squared equals C squared, right? We combine like terms by moving our C over 2 squared to the other side, okay? And then what we can do here is we know that we have 3/4 C squared. We can take the square root, and so we know that B is equal to square root of 3 over 2 multiplied by C. Okay, again, you don't have to memorize this. You just have to be able to get back there if necessary. All right. So then after we look at those special triangles, right, we can look at this thing called similar triangles, right? And that's where you have angles that are equal, but those lengths are different, right? And as we just talked about in algebra 2, okay, this thing called proportional, right? So those lengths are proportional, which means that they have a ratio that's going to be similar between them, okay? They're not the same length, but because they have the same angles, they're going to have a similar ratio, all right? A similar ratio. Another way of calling these similar triangles, you might call them congruent triangles, all right? So for example, every 45, 45, 90 triangle is similar or is a congruent triangle to every other 45, 45, 90 triangle. All right, same thing with the 30, 60, 90s. All right, in general, okay, they're going to be these congruent triangles when they have the same exact angle conformation. All right, and then another terminology thing here, just to make sure we're all clear. Okay, this little symbol here is theta. Okay, that means theta. So this is saying a right angle with an acute angle theta is similar to every other right triangle with an acute angle theta. All right, again, saying that if I have the same acute angles, again, acute meaning less than 90, all right, then they're going to be equal. Or sorry, congruent. So then looking at here again at similar triangles and these things called proportions. So these congruent angles means they're the same angles. So if I'm looking at similar triangles, this angle of A is going to be the same as the angle of D. B is going to equal E. C is going to equal F. Okay. Looking at proportional sides. Okay, proportional sides. What this is saying is A to B is going to be proportional to D to E. And A to C is going to be proportional to D to F. And then finally, obviously, B and C and E and F. All right. Again, proportional means that there's a ratio between them and it's going to be consistent. There's a ratio between them and it is consistent, right? So maybe this proportion is 1.5. It's 1.5 times bigger. Now, looking at how to maybe make an equation of proportions, okay, what we can do is we can pick two sides of any triangle. So we have, if we look here, we've got B to C and A to C. All right, we just put them equal to the same sides of the other triangle. So B to C here is going to have a proportion to E to F. Same thing, A to C and D to F, right? Different versions of that. So we can look at similar triangles and figure out if we had the exact same angles for all three, we could figure out the proportion between them. All right. So again here, moving forward away from a little bit of geometry and more to trigonometry here. There are 6 basic functions that you need to understand in order to understand trigonometry here. All right. So these are going to be called our trigonomic ratios. All right. And what the ratio is going to depend on is where that acute angle theta is located at. All right. Where that acute angle theta is located at. Right, and let me point something out here. Okay, you can have theta here where A is, or you can have theta here where C is. Theta cannot be where B is, because B is our right angle. Okay, so again, in order to be acute, it has to be less than 90. All right, and if we're looking here, I'm looking at our acute angle. These labels, opposite and adjacent, are determined based on where we're looking at our acute angle. Okay, so if my angle is here for A, that makes this my opposite side because it's opposite, and this makes it my adjacent because it's next to. All right, if C was the acute angle we were looking at, that would make A to B my opposite and B to C my adjacent. But regardless, okay, my right angle is here for B, so my hypotenuse is not going to change. Okay, so again, A to B, C to B are both considered legs, but now we get to be a little bit more specific of if it's opposite or adjacent. Again, keep in mind it's determined where the theta is. So looking at this guy here, looking at this guy here. Let me see if I. Oh, there it is. Okay. So looking at this guy here. Okay, A and B. So it says, please choose the correct answer. So again, determine based on this angle. So based on this angle, B is our opposite. All right, and A is adjacent because B is across and A is next to. All right, looking at this new angle, okay, A now becomes my opposite and B becomes my adjacent. All right, which side is the opposite? Again, just because the angles turn, you still just have to know I'm looking at angle theta, so A is going to be my opposite. Right, which side is the hypotenuse? The hypotenuse is not changing. So even though it's labeled different, right, A, B, C, okay, our hypotenuse is the one that is opposite of our 90-degree angle. So that would be side B. Woo! All right. Okay, so looking at these trigonomic ratios now, okay, so looking at these trigonomic ratios, there are 6 of them, and I'll go to Katie. Oh wait, no, you weren't in the. I shouldn't have asked you. Sarah, you were in the geotrig class at St. Lawrence, correct? How much work did you guys do with sine, cosine, tangent?
A lot.
Perfect. All right, so then I'll breeze through this. All right, so again, you have sine, cosine, tangent, cosecant, secant, and cotangent. All right, so sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Sarah, one more question here. You guys ever used that phrase, so katoa?
Yes.
Perfect. All right, easiest way for you to remember it. All right, and then the only other trick that I have is that sine, cosine. Okay, so sine starts with an S, obviously, and cosine starts with a C. So when we go to those inverses, cosecant and secant, all right, if it starts with an S, it now starts with a C. If it started with a C, it now starts with an S. So cosecant is hypotenuse over opposite, hypotenuse over adjacent, and then adjacent over hypotenuse, or again, sine, cosecant is 1 over sine. Secant is 1 over cosine, and then cotangent is 1 over tangent. All right, awesome. And so if you guys dealt a lot with this already, that means you probably know the calculator tricks to go along with this. Okay, so again, remembering that SOHCAHTOA, remembering whatever tricks you have or need for that. Okay, so then what triangle do I use, right? Really, it doesn't matter. Okay, it doesn't matter as long as you're looking at an acute angle of a right triangle and you're able to use those trigonomic ratios of, you know, sine, cosine, tangent, cotangent, cosecant, whatever. All right. So then looking at going from ratios to functions, right? Says for every acute angle input, there should be one value output. All right. So again, it sounds familiar. We're just talking about like functions here, right? So we're making trigonomic functions. For every input, there has to be one output. And by that, I mean, if I'm plugging in sine of whatever, okay, or opposite over hypotenuse, right? I have to get out one answer. I have to get out one answer here. All right. So if I'm looking at my 6 identities here, right? If I'm looking at my 6 functions, okay, there are some similarities here between 30, 45, and 60-degree angles, right? And again, I'm pretty sure this is on your study sheet, so you don't have to spend a whole ton of time memorizing these, right? But basically, there are some relationships between them, all right? And again, you can always use your identities to figure out what the values are, okay? You don't have to, again, memorize these, but there are some similarities
Start
here.
with the 45, 45, 90 triangle. The fundamental property of 45, 45, 90 triangles gives these ratios between the side lengths.
Okay, so again, if I'm looking at my 45, 45, 90, remember we talked about that in a couple earlier slides. So my A is equal to 1 over square root of 2 multiplied by C. Again, all we did was use Pythagorean theorems to figure that out, okay? So now when I'm looking at my cosine and sine, right? So if sine is equal to opposite over hypotenuse, I have my value over C. So C over C, those cancel out. So I'm left with 1 over the square root of 2, okay? And same thing for cosine, right? Since they're the same value, it's opposite or adjacent over hypotenuse, it doesn't matter. They're going to end up with the same value here, 1 over the square root of 2. The only difference is going to be, though, is in tangent. Okay, so if I've got it my opposite over my adjacent, okay, those are the same value. That's going to give me a value of 1. Okay.
Since cosecant, secant, and cotangent are simply reciprocals of sine, cosine, and tangent, you can now find these values easily.
Okay, perfect, right? So we found our first 3 easily. Then all we do is we take the reciprocal, or 1 over, right? 1 over. So we take 1 over, and then we are able to calculate the rest of those. Okay. So then if we were to do the exact same thing with our 30, 60, 90 triangle, okay, we could figure out sine, cosine, tangent, and then all we do is we go 1 over the answer we just got. So filling those in here, okay, you've got for the 30-degree angle, for sine, it's 1/2. Okay, so then obviously for cosecant, it's going to be the reciprocal of that, so that's going to be 2. All right. For cosine, it's going to be square root of 3 over 2. And then obviously for the secant, it's going to be the reciprocal of that. All right. But something I do want to point out here is that sine of 30 degrees is 1/2, and it's also cosine of 60 degrees, right? So it's also cosine of 60 degrees, right? Because again, in sine, it's going to be the opposite, and in cosine, it's going to be the adjacent. So if you think about it, a 30, 60, 90 triangle, you're dealing with the same sides of that triangle, just depending on where you're going with values. Okay, same thing. Cosecant is 2, secant is 2 for 60. All right, tangent is 1 over square root of 3 for 30, and it's 1 over square root of 3 for cotangent using the 60-degree angle. Okay, so there's some similarities here that could help you kind of shortcut if you have this table handy with you. Okay, so then knowing this, okay, we can evaluate trigonomic functions. All right, so again, all we really need to know is the equations for our sine, cosine, tangent, cotangent, cosecant, and secant, and then obviously knowing our Pythagorean theorem here.
Suppose you know that sine of theta equals 1/4. To find the values of the other 5 trigonometric functions, start by drawing a right triangle and labeling the angle theta. Here we assume that theta is acute.
Oh, okay, and again, one thing before I fast forward here, okay, again, if it says sine of theta is equal to 1/4, okay, or 1/4, right, I always write it as 1/4, okay, just kind of a prequel there, 1/4, and you have to draw, again, a right triangle. Sine, cosine, tangent, all of those deal with right triangles. So if you're not drawing it as a right triangle, you're messing up here. So right triangle, then you assign your angle, assuming that it's less than 90 degrees, right? And then we can, like you said, plug in for 1/4.
Since sine theta equals 1/4, you can write a 1 on the side opposite theta and a 4 on the hypotenuse. You do this because you know that the ratio of those sides has to be 1/4.
Okay, has to be 1/4. So it has to be 1/4. Again, sine is opposite over hypotenuse, so opposite over hypotenuse.
Now you need to calculate the measure of the third side, labeled A.
All right.
This is where the Pythagorean theorem will be used.
So again, knowing that a squared plus b squared equals c squared, okay, we can write that. This means that a squared is equal to the square root of, oh wait, sorry, a squared is equal to 15, right? Because 4 squared is 16 minus 1 squared is 15. Okay, so then solving for a gives square root of 15. And again, remembering that, yes, normally when we would do this, when we take the square root, if we were solving for our polynomial, we'd have plus and minus square root of 15. But obviously, we can't have a negative value for a triangle, so it has to be just that positive square root of 15. And again, this is that one input, one output. Okay, so a can only be one value here.
Now that you know all 3 sides of the triangle, you can calculate the other 5 trigonometric ratios.
Okay, perfect. Since we know one, we can figure out all of them, okay, using our ratios there. All right, using our ratios, using our understanding, and using Pythagorean theorem. All right, so then again, assuming that this one, and I know you guys can't do drag and drop, I believe, on your iPad, so I'll walk you through this one, even though you guys said you know this. But sine opposite over hypotenuse. So opposite, 2/7. Okay, 2/7. And when I use my Pythagorean theorem, I'm able to figure out that this is the square root of 45. All right. So then knowing that sine is this, personally, the next thing that I do is just go straight to its reciprocal. So I go to cosecant. So that would be 7/2. All right. Now cosine is going to be my adjacent over hypotenuse. So my square root of 45/7. All right, so then again, personally, I go to its reciprocal, 7 over the square root of 45. Then for tangent, okay, for tangent, it's opposite over adjacent. So 2 over the square root of 45, and then its reciprocal there. Okay. All right. So then going back to the tree problem here, okay, supposing we're trying to figure out the height of a tree, okay, we're able to look at the sun casting a shadow, we're able to use our understanding and able to calculate
notice that
it.
the tree is casting a shadow and that the length of the shadow varies depending on the position of the sun. At a particular moment in time, you estimate that the angle between the ground and the line that connects the tip of the tree to the tip of the shadow is 55 degrees. You measure the distance from the tip of the shadow to the bottom of the tree to be 20 feet. Remember that you are trying to find the height of the tree, so call that x. Since tangent is defined as side opposite over side adjacent, You see the tangent of 55 degrees is x over 20. Use your calculator to approximate tangent of 55 degrees and then solve for x. In the end, you find that the tree is roughly 28.6 feet tall.
Okay, right? So knowing that, okay? And again, that's just knowing what you have, knowing the equations that are at your disposal, and filling in for the appropriate values there. All right? So then kind of in summary here, we've got right triangles, and we're talking about Pythagorean theorem, understanding those special triangles for 45, 45, 90, 30, 60, 90, and then understanding our trigonomic functions of sine, cosine, tangent, cotangent, cosecant, cosine. All right, so if we look here, decide how to measure the following unknowns. Okay, so if we look at this, we can use Pythagorean theorem to find y, okay? To find y, not to find x, okay? But we can look here, if we're looking at x, okay, we can figure out x as the opposite over the adjacent, so we can figure out tan of x. All right, and we also know that if we're looking at, let's say, cosine would be 5 over y. Cosine would be 5 over y, so not 6, so that's incorrect. But we know that sine would be 6 over y. Okay, so there's 2 more problems here that I'll let you go through and check. But basically, again, the key here is for you to know what you have, know what's at your disposal, and plug in the appropriate values. Okay, so looking at our study guide here, briefly, looking at our study guide here. So again, we have the angle, or sorry, the side opposite of our 90-degree angles are hypotenuse, and then those 2 other sides are called our legs. All right, and then what it's saying is the sum of the squares of the lengths of the legs is equal to the square of the hypotenuse, or a squared plus b squared equals c squared. All right, in a right triangle, if the lengths of the side are not opposite to the right triangle equal to 3 and 4, then it would be equal to 5. Again, 3 squared plus 4 squared equals 5 squared. And then the Pythagorean theorem cannot be used for triangles other than right triangles. Okay. So again, a squared plus b squared equals c squared. And then when we solve, when we take the square root of both sides, again, we can only have the positive value and not the negative. So again, remember, when we take the square root, we are now only dealing with the positive values because we're talking in the real world where we need an actual positive number. All right, so then looking at page 4 and page 5, what this is saying here is those are the special cases. So the legs are equal to 1 over square root of 2 in a 45, 45, 90. And then the shorter leg of a 30, 60, 90 is 1 over 2, where the longer leg is 3 over 2. Okay. So then triangles whose angles correspond are similar. Okay. We also call them congruent triangles that have equal angles and corresponding side lengths. Those are congruent triangles. All right. And then between those similar triangles, we have a scale factor, right? Or a ratio, how much we're going to go up or down by. Okay, then our 6 basic functions, knowing this now, are sine, cosine, tangent, cosecant, cotangent, and cosine. All right. Any ratio with those interior angles, we call them trigonomic ratios. And then looking at this, we can tell that if this is our angle theta, B is adjacent, A is opposite, and C will always be the hypotenuse. All right. So then again, knowing our relationships, opposite over adjacent or whatever, right? So your SOHCAHTOA, and then understanding that we have those reciprocals. Okay, so just taking 1 over those values. And then filling in your table here. Again, this could just be very, very helpful for you to have on hand so you don't have to go through that every time. But if you don't have it on hand, again, you can always just go through and redo your trigonomic functions and your Pythagorean theorem to get these values. All right. So then for this one here, it says suppose cosine of theta is equal to 3 over 5. So the thing that they're not showing that they would have done is they would have drawn a triangle here. Okay, they would have drawn a triangle, make it a right triangle, add an angle on either side, right? Depending on whichever one they want. And then they would have filled in values. So for cosine, this is adjacent over hypotenuse, right? They would have filled that in and then been able to calculate the rest of them there. All right. And for this one here, again, the big thing for me is picking out what is necessary out of this word problem. So reading it once, picking out what's necessary, draw a picture and then fill in as you go. Right, so again, it says connects the tip of a shadow of the building to the tip of the building is 75 degrees. Okay, the distance from the tip of the shadow from the bottom of the building is 50 degrees, right? So that's maybe not obvious until you start drawing what the heck it's saying, then you're gonna realize, oh, it's a right triangle, okay? So just maybe some helpful hints there. Moving forward with this guy, just looking at our checkup here quickly. All right, looking at our checkup here quickly, again, just being able to use those principles to determine the side lengths and making them, again, positive values. So to find the side lengths here, you have many, many different methods that you could do, okay? So you could plug in those values, you could use sine, cosine, cotangent, and let's go, who haven't I called on? Yarlesk. Have you guys, when you did your geotrig, did you guys talk about looking at like method 2 and method 3 here? Did you talk about why that works?
I think so.
Okay.
It looks familiar.
Okay, perfect. Right, so all this is here is just being able to move values around, right? So knowing that this is a ratio and knowing that this is equal to something, all it's showing is that I can do, right, that cross product that we talked about, right, the multiplying diagonally. So if I kind of draw this out here kind of crudely, sorry. If I were to put this over 1, this is saying, okay, a times by 1 and 25 times by cosine of 35, right? So that's all that's saying, 1a multiplied by this guy, all right? If I were to do the bottom here, I would still multiply or cross multiply these guys, but before I could get there, I would have tangent is equal to my 14.34 times by 1, and then I would divide my tangent to get it on the other side, right? So there's just an extra step involved in this one, okay? So just an extra step there. But it's still using that cross product principle that we talked about. Okay. But if that's confusing to you, by all means, you can stick to method 1, which is just our normal Pythagorean theorem. All right. Again, same thing. This is just making sure you can do things in your calculator. And since you guys have done that, I'm not going to spend time going through it with you. If you've got specific questions, by all means, reach out to me or your Apex teacher or one of those online tutors, and we can help you. But I don't want to spend too much time on it. So then, obviously, here for this guy, okay, it's saying find sine. Okay, well, we only have 2 sides of our triangle. We need our third side. So obviously the first step there is using Pythagorean theorem, right? Then we have all 3 sides. Then we can obviously find sine, cosine, tangent. I personally, again, once I find those 3, I just go 1 over whatever my answer was. I don't waste time necessarily going all the way through the process again if I don't have to, okay? And all right, so then here looking at the last couple, again, this is just straight up off of your table or using your calculator, right? Using your calculator to actually verify that that is what it is, right? Just typing in sine 30. And then again, the word problems, okay? Again, the word problems, just figuring out what it's asking you, drawing a picture, and then moving forward there. SOHCAHTOA, right? Awesome. So that's what I use. So that's pretty much this whole first unit here, and I'm glad that most of us, if not all of us, have had some experience in this. okay? The only other reminder I want to make sure is that you are in your correct calculator mode. All right, and by that I mean on your calculator, up at the very top, you have that second button. If you click on the button next to it, it says mode. All right, when you're dealing with degrees, you need to make sure that your calculator is in degrees. Okay, and so it should be the thing that is highlighted. Mine is highlighting black. All right, you need to make sure that when we're working with degrees, you're in degrees, because throughout this semester here, we're going to switch also to radians. Okay, so you need to make sure that you're on the correct unit there. All right, so we will have this 1.1.3 quiz. So hopefully, since you guys know it, it's not too much work for you. All right, and then the last section we're going to talk about here is angles and radians. So exactly what I just said. We're going to deal with radians here. All right, so we have lesson 1 and lesson 2, and then we're going to be done with pre-calc for the day. All right, so dealing with angles and radians though, okay, like all functions, they have inputs and outputs. And we have things called central angles, okay, central angles. And we'll learn more about that, but the central angle is an angle with an endpoint located in the circle's circumference, okay, and with a vertex at the circle's center. So what that means is its endpoints are on the outside of the circle, all right, and it's got a point, a vertex point, right, that midpoint there at the circle center, all right. And who else haven't I called on yet? Dante, how much work did you guys do in geotrig with radians? Dante, you there? Ew. Okay. Quinn, why don't you help him out? Do you guys do a lot with radians, a little with radians, none at all?
My class didn't do much with radians.
Okay, let's ask another class then. Yarles, did you guys do a lot with radians?
We didn't do a lot either.
Okay, that's totally fine. Perfect. So now we're learning something new here. All right, so radians have to deal a lot with this thing called pi, right? And you guys know that pi is like 3.1415, whatever. Keep going on forever. It's this number here. All right, so we're gonna look at how do we take these angles and go from degrees to this thing called radian, and it's going to have to do with this thing called pi. All right, so before we can get started here, we need to get a little bit more specific with our definition of angle. Okay, so looking here, angle is the union of two rays having a common endpoint. All right, so a ray is a line with an arrow. Right, so usually we show a ray as a line with an endpoint that looks like an arrow. Okay, so obviously we need two of them, because that's what it said, and the angle is the end point. So where those two connect. So A here is our angle. All right, and if we just have this, we write it as angle A, right? So showing a little angle symbol shows it as angle. All right, and if you're ever going to go on in the future, maybe, okay, with more math stuff here, okay, again, being careful that this is not an inequality, right? And to show the difference here, we draw it as a big angle. So you can see here that the angle goes from the top of the A to the bottom of the A versus an inequality would be much smaller. So it's not saying less than A, it's saying angle A. All right, and looking at even further, okay, if we picked points on the ray, so we call that B and C, we could call this angle BAC, right? BAC. Or you could call it CAB, right? The only requirement there is that obviously you have to use all the letters and that A has to be in the middle, right? So again, BAC or CAB. Again, I'm just tracing because that's how you would read it. Angle B to A to C or C to A to B. All right, so then looking at a couple angles that we might encounter here, all right, you have acute angles, all right, that's anywhere from 0 to 90 degrees, Obtuse angles is 90 degrees to 180. All right. A straight angle is 180 degrees. Right? It's perfectly 180 degrees. A zero angle means we haven't moved at all. And then this thing called a reflex angle. It's anywhere from 180 to 300 degrees. Okay, anywhere from 180 to 300 degrees. All right, so again, acute, small, obtuse, large, reflex, even larger, goes past our straight angle, but it's not a zero angle. All right, so looking at our different types of angles here, okay, I'm not going to spend too long. Acute, obtuse, reflex, obtuse, acute. Hopefully this is not too terribly difficult here. Again, it's just knowing terminology. All right, but I know you guys can't do the click and drag, so I want to make sure that we cover it. All right, so again, acute being smaller than 90, obtuse being 90 to 180, and reflex being anywhere from 180 to 360. All right. So then looking at here, degrees, minutes, and seconds. Okay. I've never personally looked at things as degrees, minutes, or seconds, okay, or as a decimal amounts, but it's a different way of writing angles, okay? It's a different way of writing angles. It gives alternatives for writing decimals, okay? So instead of having to use a lot of decimals that are maybe nasty looking, we can use this degree, minute, second form of writing an angle, all right? Now, we have to get comfortable with converting between these forms here, though, okay? So when we're looking at our degree, minute, second.
In an entire circle, there are 360 degrees. If you start with the zero angle and then draw more rays with endpoints on the circle, you will be drawing angles that increase in measure from 0 degrees all the way to 360 degrees.
Okay, so obviously, like we said, 0 all the way to 360.
What do you do if the measure of an angle is not an integer? You use the same approach that you take when measuring linear distance. You might say, for example, that something is 15.75 yards, or you might say that it is 15 yards, 2 feet, and 3 inches long. The same thing is done with angle measure using degrees, minutes, and seconds. To do this, you need to know that 1 degree equals 60 minutes and 1 minute equals 60 seconds.
Okay, so again, thinking like a clock, okay, we're saying 1 degree is equal to 60 minutes, all right? 1 degree is equal to 60 minutes, and 1 minute is equal to 60 seconds, right? We know that 1 minute is equal to 60 seconds. All right.
Suppose, for example, you have an angle that measures 20.32 degrees, and you want to express this measure using degrees, minutes, and seconds. How do you do this? You know that you have 20 whole degrees plus 0.32 of a degree. How many minutes would 0.32 degrees be? Since there are 60 minutes in a degree, you can find out by multiplying 0.32 by 60. This tells you that you have 19 whole minutes plus 0.2 of a minute. Then, since there are 60 seconds in a minute, you can find out how many seconds are in 0.2 minutes by multiplying 0.2 by 60. Now you know that 20.32 degrees equals 20 degrees, 19 minutes, and 12 seconds.
Okay, so again, the key there is just knowing those relationships. So we said at the beginning, 1 degree is equal to 60 minutes, all right? 1 degree is equal to 60 minutes. And 60 minutes is equal to, 60 seconds is equal to 1 minute, right? So we have 20 whole degrees, like he said, so you leave that 20 alone. Then we have 0.32 of a degree. So we just use our mathematical relationships. And something that I wish they would have done is I wish they would have written this out like you would have seen it in your chemistry class, right? So this would have said, or this should have said, 0.32 degrees, and maybe let me try to write this out in my calculator for you guys. So let me share this out. Okay, so what I wish they would have wrote this as is it should have said 0.32 degrees multiplied by, or I can write it as an X like you're used to seeing it in chemistry class, okay, multiplied by a fraction of 60 minutes per 1 degree. Or in every 1 degree, there's 60 minutes, right? Because what this would have done here is cancel degree, cancel degree. So I'm left with 19.2 minutes, right? And how they're writing that is 19.2 with a single apostrophe, okay? So then what it's saying is, okay, I've got 0.2 of a minute or 0.2 minute, all right? And what they should have, again, shown you is multiply by my fraction of 60 seconds in 1 minute. This would have left me with my 12 seconds or 12 with two apostrophes, right? Or a quotation mark. So that's what I wish they would have wrote it as, okay? But basically, again, it's understanding that this is the relationship and being able to plug in what you have.
You can check your work by going the other direction. If you start with 20 degrees, 19 minutes, and 12 seconds, you can reason this way. 12 seconds is the same as 12 3600ths of a degree because there are 60 seconds in a minute and 60 minutes in a degree, so there are 3600 seconds in a degree. 19 minutes is the same as 19/60ths of a degree because there are 60 minutes in a degree. When you do this calculation, you obtain 20.32 degrees.
Okay, and again, what again, I wish they would have showed you. They kind of show you it there in the condensed form, but I've got 12 seconds. So if I were to multiply that by my fraction or my ratio that I know, I've got 1 minute per 60 seconds. Well, now I've canceled seconds out on top and seconds out on bottom, but I'm left with this thing called minutes. I know that I need to cancel out my minutes, and I'm trying to get to degrees. So what's the relationship I know that's going to take me from minutes to degrees? Oh, well, 1 degree is equal to 60 minutes. Okay, so again, knowing this, it's like saying 12 times by this fraction and this fraction, or saying 12 divided by 3600. So this has left me with some number in degrees. Because again, minutes cancel here, minutes cancel there, seconds cancel there, seconds cancel there. All I'm left with is degrees. So again, working backwards, being able to work backwards. All right. So then here, if we keep moving forward, trying this for ourselves here, I'm going to let you guys try this one on your own. Okay, I'll let you try this on your own. But again, all you have to know is these two relationships. There's 60 minutes in a degree, and there's 60 seconds in a minute. So again, I have my 0.45 here. All right, I've got my 0.45, and shoot, maybe we'll just do it together. All right, because we got time. So if I've got 0.45, all right, and unfortunately, when I do the calculator, I can't write it all out for you guys, so sorry. But I've got 0.45 a degree, all right? So I've got my degree, and I'm trying to change it to minutes. So I guess first off here, this should be 55 degrees, because that's a whole degree. Now when I'm looking at my minutes here, I've got 45, and I'm going to divide that by, oh, nope, sorry, multiply that by 60, because there's 60 seconds, or sorry, there's 60 minutes in a degree. So it's telling me 27 flat. So 27 by itself. So this should be 27 minutes and 0 seconds. And this angle is an acute angle. All right. So that's how you would have answered that. 55, 27, 0, and it's acute angle. All right, this one here, we know that it's an obtuse angle. All right, we know that it's 134. Now we have 26. Okay, so we've got 0.26, and I'm going to multiply that by my 60 to see how many minutes I have. Now I've got 15.6 minutes. So I know I have 15 minutes there. And then I take that 0.6 and I'm going to multiply it by a 60 again because I want to get that into seconds. And I've got 36 seconds. So again, 134 degrees, 15 minutes, 36 seconds. All right, and I'll leave the last two for you guys to try there. All right, but that's how you walk through that process. All right, so then now looking at this thing called radians. All right, so we can do this degrees, minutes, seconds way of showing angles. We can obviously just show it in degrees, and now we can do this unit called radian. All right, so again, like I told you, you have to be careful that you're in the right mode. All right, so on most graphing calculators, under the mode button, you can switch between degrees and radians. You cannot go degrees, minutes, seconds, unfortunately. Sorry. All right, but radians are actually a common unit. So if we look at what radians actually are, okay, if we were to draw our circle here, a radian in a circle is in a circle of radius r. That's what we're showing here. So we've got 1 radian, okay, and it's got a radius of r. All right, and when we look here, the piece of the circle between those intersection points is called an arc. All right, so right here, r is called an arc. R here in blue is called an arc. Now, an angle of 1 radian determines an arc equal to the length of the radius of the circle. All right, so I know that that's confusing here. So what that's saying is if I have this angle and it's at 1 radian, that means that my distance in blue is going to be the same as my distance in red. All right, but obviously it's a little bit more difficult to see because in blue, this is curved here, and in red, this is a straight line. So if I'm looking at it, it doesn't look like they're the same length, okay? But that's where this notion of radians come in. So again, 1 radian, or a radian, is where you have the arc equal to the radius. All right, you have the arc equal to the radius. All right, so again, in blue, arc, red, radius. Okay, and since they're the same value, this angle, whatever it is 1 radian. All right, and how do we relate radians and degrees? Okay, so the radius, the relationship between them in geometry, you might have talked about this, maybe not. The circumference of a circle is 2 pi, right? 2 pi. Or it's 2 pi r, right? Technically, it's 2 pi r. But if we have a radius of 1, we just call it 2 pi. All right? So when we're calculating the circumference of a circle, right, the equation is 2 pi r. But if we have a radius is equal to 1, we just call it 2 pi. All right? So if you can remember 2 pi r equals 1, it's just 2 pi, then this is going to be easy for everybody. All right? So looking at degrees and radians.
Because the circumference of a full circle is 2 pi, the circumference of a half circle is pi. Thus, there are pi radians in 180 degrees.
Okay? So pause here. All right?
Thus, the
Okay, so we said this entire circumference is 2 pi. The entire circumference is 2 pi. All right?
circumference of a half circle is pi.
So if this whole thing is 2 pi, then this one side is pi and this other side is pi, right? So 180 degrees is equal to pi.
Thus, there are pi radians in 180 degrees.
Okay? So there are pi radians in 180 degrees, right? So we're saying we have pi radians in 180 degrees, because again, this whole circumference is 2 pi. Whole circumference is 2 pi. So 1 radian equals 180 divided by pi, and pi over 180 radians equals 1 degree.
Using your calculator, you can approximate 1 radian to be 57.3 degrees. To convert from radians to degrees, multiply by 180 over pi. To convert from degrees to radians, multiply by pi radians over 180 degrees. Keeping the units in mind, you can see that these formulas will be easy to remember.
All right. Okay, so again, it's knowing this equation right here. All right, so we know that 1 radian is equal to 180 divided by pi. 1 radian equals 180 divided by pi. All right, so we can know that converting from radians to degrees. So if I started with 57.3, okay, I can multiply by 180 degrees over radians. Oh, sorry. I just confused you. I messed up. So sorry, if I have radians, okay, I multiply by this 180 degrees over pi radians. Again, because radians on top would cancel with radians on bottom. It's just simple unit conversion here. All right. Oppositely, if I started with my 57.3 degrees, I would multiply by pi radians over 180, right? I'd multiply by pi radians over 180. So what you can see here,
Keeping the
okay, I start with 2.34 radians. Okay, so I'm going to go radians, cancel with radians, all right, and then I'm going to be left with my 180 degrees. All right, so 2 times by 180 degrees gives me this 134.07 when I divide by my pi there. So 2.34 multiplied by 180 divided by pi. All right. Oppositely here, if I'm converting 75 degrees to radians, I have degrees multiplied by radians over degrees, so my degree symbol will cancel, and then I do 75 times pi divided by 180, and I'm left with that 1.31 radians. All right. So then here, measured in radians, measured in degrees. Sorry, radians measured in degrees. Okay, so you're going to be able to convert using that 180 over pi. If you're going from radians to degrees, and then you've got pi radians over 180 when we're going from degrees to radians. So if we're looking at, let's go with things that are measured in radians. Okay, we're going to multiply by, and let me pull this up here. So when we have radians, we're going to take our radians, we're going to multiply by our 180 over our radians. Or I guess I should say 180 degrees over our radians. So I have 0 here. 0 times by anything is going to give me 0. All right, so I've got 0 degrees. I've got pi over 6. Where's my pi symbol? Oh, there it is. All right, perfect. All right, so 180 degrees over pi radians. Okay, got an equal degree. So when I'm looking at pi over 6, I'm looking at pi over 6. So what this is going to show here is I've got sorry, I know this is taking a while, so I'll only do a couple examples here and I'll let you try the rest. So, but I've got pi over 6 multiplied by 180 over pi. Okay, 180 over pi. So what ends up happening is I'm left with the pi's canceling out. I just have 180 divided by 6. So if I plug that into my calculator, 180 divided by 6, I'm left with 30 degrees. All right, I'm left with 30 degrees there. All right, so then I can kind of do the same process there. If I've got pi over something, okay, those pi's are going to cancel out. So I'm left with just 180 divided by 3 for the next one. So this is going to give me 60. Okay, But what becomes more difficult is if I have 5 pi over 4, something like 5 pi over 4. So what that's going to look like again is 5 pi over 4 multiplied by 180 over pi. Okay. So again, pi's cancel, but I'm left with something maybe not as nice on the top. 5 times by 180 divided by 4. Still pretty simple here, just one extra step. So 5 times 180 divided by 4 gives me 225, right? Okay, and so on and so forth. So then when we're moving in the opposite direction, okay, when we're going from degrees to radians, we're going to use the process degrees multiplied by pi radians over 180 degree. Right? So if I look at this first one here, I've got 90. So 90 degrees. Oh gosh almighty, sorry. Multiplied by, awesome, pi over 180. So actually what I do is I just have 90 divided by 180. All right. And that's going to leave me with a 1/2, right? So I actually have just pi over 2 for that one. Okay, so that's pi over 2. All right, and then I can follow the exact same process, even for something as large as maybe 330. So if I have 330 degrees, I'm going to multiply by my pi radians over 180. I just do 330 divided by 180 multiplied by pi. That's going to give me 1.833. So what that ends up being, I believe, is 11 pi over 6, right? 11 pi over 6. All right. So again, being really, really careful not to mess up, okay? So you've got to make sure you're putting all the symbols, okay? You've got to make sure that you're using the correct equations. Don't just run through it here. And then always make sure you check to see what mode your calculator is in, especially when we're dealing with like a unit like this where you got to go back and forth. You've got to be really, really careful there, all right? And they point out here, if the degree symbol is not there, assume the number refers to a radian measurement. Okay, if the degree symbol is not there, assume that your number is a radian. Okay, so that also means when you give your answers on a computer, if it's one where you have to type it in, if it's a degree and that degree symbol's not already in the answer, you need to make sure that you type that in there, or it might mark you wrong. Okay, it might mark you wrong. All right, so again, walking you through, again, mode, okay, you just make sure you hit radian. Last couple things here, looking at arc length.
Consider a circle of radius r. The central angle theta, measured in radians, determines an arc of this circle. How long is the blue arc? The length of an arc is defined to be r times theta, where theta is the measure of the central angle in radians.
Okay.
For example, if you have a circle of radius 5.
Oh, I guess I should have paused there for a second. All right, so again, remembering that when we were talking, a circumference of a circle is 2 pi r. 2 pi r in general, okay? But when we were talking originally, we were assuming that r was equal to 1. All right, we were assuming that r is equal to 1. All right, but when we're going forward, if you have a specific circle and it tells you a specific arc length, you have to take that into account. Or you have a specific radius, you have to take that into account.
For example, if you have a circle of radius 5, and if theta equals 3 pi over 4, Then the corresponding arc length is 5 times 3 pi over 4.
Okay, so again, when we're calculating the arc length, all right, that blue, all right, we know our radius is 5 here. Okay, so we have to multiply our radius times by our angle. Our radius times by our angle. So we would multiply 5 times 3 pi over 4. Again, pi is a symbol, yes, but it's still a number. So you can calculate that and get a value. And it's hard to see here with this. So
Then the corresponding arc length is 5 times 3 pi over 4.
You see that squiggly lines here? Those two squiggly lines, that means approximately equal to. All right, so that means that they rounded that value. All right, so if we look back here at the Ferris wheel that was in the beginning that we kind of skipped over, all right, you can clearly see that it's got different cars and it's got, we can calculate the length based on the values that we know. So if we know that the radius of the Ferris wheel is 25 feet, and we are trying to look at the distance between different cars, right? We can use our angle that we know of 30 degrees, and we can calculate our arc length. Okay, again, figuring out that this is, and we can figure out what our degrees is in radians, right? So what is 30 degrees in radians? And then multiplying by our radius here of 25. All right, so what this would look like here. All right, we know that the central angle is 30 degrees, but we got to convert that, like I said, to radians. All right, so we would use that formula. Oh, sorry, it's asking us to pick the formula. So if we're going from degrees to radians, we have to make sure that we have degrees on bottom, right? So that the degrees and the degrees cancel out. All right, so then when we're left, we have radians, okay? Now we use our arc length formula. All right, so our arc length was, hold on. It's saying arc length is, no, I had it. Oh, sorry. I clicked the right one there. Oh, I was confused. Sorry. I thought it was telling me I clicked the wrong one because I know that that's right. Sorry, the arc length formula, what that's saying is we multiply our radius by our degrees, or our radians. So our length here is 25. So that's why when I clicked 25 originally, that's the right answer. And then we multiply it by our radians. Okay, so it would be 25 times by pi over 6. So if I plug that into my calculator, 25 times by pi divided by 6, that's going to give me about 13.09. So that should be my answer there. Sorry, this was confusing. So I'm glad we worked through that together. So what this is saying here is that I take 25, which was my radius, and I multiply by my angle, which is now in radians. Okay. All right. So then just a quick review here. All right. Knowing the difference between our minutes, our seconds, our degrees, right? Radians, different types of angles here. Okay. So this is one that you guys can do. So I'll let you do that on your own. But let's take maybe 30 seconds here and fly through the study guide and fly through the quick checkup here, so then we're done. All right. Oh. All right, so looking at this here, an angle is the union of two rays having a common endpoint. Okay, this could be called PNM or MNP. Doesn't matter as long as N's in the middle. All right, acute is between 0 and 90. Obtuse is between 90 and 180. Reflex is 180 to 360. A 0 obviously is 0. And then a straight angle is 180 degrees, or a straight line, right? So you could figure out which one is which. And we found out that we can convert from fractions of degrees, right? So instead of saying, 20.25, we can do this degrees, minutes, seconds formula, where we have 1 degree is equal to 60 minutes, 1 minute equal to 60 seconds. So then we can calculate based on that. And we did an activity through that. All right. And we can go either way, but again, the reminder for this is it's just basic unit cancellation, right? It's basic dimensional analysis that you guys spent a long time doing that in chemistry. Okay, so it's just basic dimensional analysis. Then when we're looking here about radians, okay, so the angle of 1 radian determines the arc equal in length to the radius of a circle. Okay, I know that's confusing. So basically what that's saying is when I have an angle of 1 radian, that means that my arc length, that curved part, is equal to my radius. All right. So 1 radian is approximately equal to 57.3 degrees. All right, and how we can convert from one to the other is using these 2 equations. So if we're going from radians to degrees, we have 180 degrees over pi radians, and the opposite, pi radians over 180 degrees when we're going to radians. And again, it's unit cancellation. So if I have radians on top, I need radians on bottom. Simple as that. And then again, going back and forth, this should just be simple, again, simple unit cancellation, making sure we've got this right. And then what happens here is if the radius is not exactly 1, okay, if it's not exactly 1. So what that means is the arc length is defined as r theta, where theta is the measure of the central angle in radians. All right, and when r is equal to 1, it's simple, it's just the same thing. All right, but if it's not 1, we have to find our angle in radians, and then we have to multiply. All right, so again, what we have to do is we find our angle in radians, perfect, so the arc length is equal to the radius times by our angle. All right, and again, with word problems, personal suggestion, make sure you actually write them out. Okay, make sure you write them out, and draw a picture if you need it. All right, 30 more seconds. I know we're at 11:30, so bear with me here, and then we're done. Okay, so again, labeling the angles, hopefully not too terribly difficult here. Converting the angles, okay, that's, again, unit cancellation here, but just knowing 60 seconds equals a minute, 60 minutes equals a degree. All right. Converting from radians to degrees, that's 180 over pi radians or pi radians over 180, all right? And then being able to figure out what the arc length is. Again, that is radians, whatever your degree is in radians, multiplied by your radius, okay? So for this one, the arc corresponding to the central angle of pi over 3 of radius 6 inches. So that one would be 6 times that number, right? Or just 2 pi inches. All right, and again, this one, be careful, it's talking about inches, or this one's in feet, or this one's in inches. You have to include those values when you're giving your arc lengths, okay? And then again, that's pretty much it, just being able to work forwards and backwards. So for this one here, it's saying the measure of the angle is 1 radian, okay, if it's 1 radian. So then being able to figure out the rest of these, okay? So we're done with pre-calc here, okay? So you have just these 2 units and 2 quizzes to do for pre-calc tonight, okay? So again, try to keep up, at least stay on track with us, kind of every week, be at the same point, and we're gonna, again, cover about 2 per day that we are in class for pre-calc. So keep up with that.